Frequency stability comparison of LC and RC oscillators. By the way, myself Nikhil B at Case Rangaswamy College of Technology. LC oscillator fundamental. Resonant tank circuit LC oscillator utilizes the energy exchange between inductors and capacitor at a resonance frequency f naught equal to 1 divided by 2 pi root of LC. High Q factor. The quality factor Q determines the selective phase noise performance. Typically, value range from 50 to 500 for discrete LC tanks. Common topologies. Colpitts, Hartley, and Clapp configuration are widely employed, each offering distinct trade-off in stability and harmonic content of the LC oscillator fundamentals. What is frequency stability? Frequency stability quantifies an oscillator ability to maintain a constant output frequency over time despite environmental variation and component aging. It is expressed as fractional frequency deviation, del f divided by f naught. Critical parameters include short-term stability, phase noise, and long-term instability, drift aging effects. Why it matter? In communication system, timing circuit and instrumentation frequency instability directly impact system performance, causing bit errors, time jitters, and measurement uncertainty. Applications such as RF transceivers, clock generators, and frequency synthesizer demand a rigorous stability specification. RC oscillators fundamental. Phase shift network. RC oscillator generate a sine wave using resistor capacitor phase shift network that provide 180-degree phase shift at oscillator frequency. Common architecture. Weinbridge phase shift and twin T configuration are relevant and particularly for audio and low frequency application below 1 MHz. Integration advantages. RC oscillators are easily integrated in IC forms, avoiding bulky inductors, making them cost effective for a chip. Stability performance comparison. LC oscillator. Superior short-term stability with phase noise typically -130 to -140 decibels offset. High Q factor resonator minimize jitter and noise contributor. Temperature coefficient depends on L and C material properties. Frequency range typically 1 MHz to several GHz. RC oscillators. Moderate stability with phase noise around -80 to -100 decibels offset. Low Q factor result in broader phase noise spectrum. Temperature sensitivity driven by RC component. Tolerance of frequency range typically sub -H to 1 MHz. Source of instability. Temperature variation. Design trades-off and application selections. Choose LC oscillator for RF microwave application, low phase noise requirements, high frequency stability demand, communication radar and instrumentation. Weighing both spectrum permits discrete integrators. Choose RC oscillator for audio and low frequency application, cost sensitive, high volume production, full integrated IC solution, function generator and waveform synthesis when inductor are impractical or costly. Stability enhancement technique. Crystal resonators. Adding quartz crystal to LC configuration achieve ultra high Q and exceptional stability. Temperature compensation. Design maintains stable operation temperature, reducing drift plus or minus 0.1 ppm over wide range. Phase lock loops. Based frequency synthesis locks RC or LC oscillator to stable free reference, combining flexibility with precision. Voltage regulation. Low noise LDO regulators minimize supply induced frequency variation, improving overall stability metrics significantly. The stability enhancement technique. LC oscillator excels in stability. High Q factor resonator delivers superior phase noise and short-term stability, making LC topologies ideal for RF and precision application where frequency accuracy is paramount. RC oscillator offer integration. RC design trades stability for simplicity, cost-effective, and IC compatible, suitable for low-frequency application with relaxed stability requirements. Design context matter. Oscillator selection must balance frequency range, stability specification, cost constraint, and integration requirements. Advanced techniques like temperature compensation and PPLs bridge performance gaps. These are the parameters of LC and RC oscillators.